Good morning, everybody. Welcome to Using Machine Learning and Building a Prepayment Model. We'll give it another minute before we get started just to make sure a few more people can log in. Prior to that, let's just review a few housekeeping details to ensure this webinar goes smoothly. Just so you know, everyone is muted during the call to help us prevent background noise and to make sure we can all hear clearly. If you have any questions, you will see in the GoToWebinar panel a questions box. Feel free to ask anything in there, and we will get to them at the end during our Q&A session. Last thing is you'll be given a short survey after the conclusion of this webinar, so please fill it out to help us get some feedback on these events. To briefly introduce our speakers, we have Fan Zhang, Director of Model Development, Lei Zhao, a Quantitative Modeling Analyst, and Janet Joswick, a Managing Director presenting today. Without further ado, I'm going to hand this off to Fan.
Okay. All right, thanks, Pat. So for today's agenda, we will go over the use of machine learning to solve or at least help alleviate the challenges of prepayment modeling. We'll walk through the process of setting up a simple prepayment model and then fine-tuning it. And then we'll talk about techniques for getting comfortable with the black box nature of these models. So why do we want to bother with machine learning? As you all probably know, behavior modeling is very difficult due to a number of reasons. The historical data is limited. We can't just generate new loan data on the fly. We have different kind of eras in the prepayment history that behave very differently, like pre-crisis, post-crisis, that limits the amount of data available. There are many reasons why someone might choose to pay their mortgage early. Some factors are well-researched, well-known, intuitive. Some are not. We kind of have to determine from the entire universe of all the inputs available which ones to use. And even once we determine the primary prepayment drivers, we still have to determine what kind of function to model those as. All of these decisions are very time-consuming, and there's always difference in the performance due to how well we can select these parameters. Machine learning can help with this. So by their nature, they're very good at dealing with large amounts of very high-dimensional data. They will, from the data, learn the functional forms of the model so that we do not have to specify those manually. And whenever there's new data, it's very easy for the machine learning algorithm to adapt to it. So machine learning has already shown superhuman performance in many areas. An important one of which is when Google's AlphaGo beat the world champions at Go. And this was a problem that people were still saying at the time, 10, 20 years, there's no way for the machine to beat a human. It just shows that when machines are able to learn on their own, they're very powerful, especially in this case when Google trained a new version of AlphaGo using no human input and no historical data. Just by playing itself, it was able to beat the previous version of AlphaGo in only a few days. When thinking about machine learning, one important thing is to pick the machine model to be used. There are many different machine learning models, each with their own strengths and weaknesses. So we basically tried some of the most popular and most powerful methods available today. These include gradient boosting, which is a very strong technique whereby usually you start with something like a decision tree that's simple. You basically build a tree and then look at the air and then build another tree on that air, which then reduces that air, et cetera, until you get to a specified point. Probably the best implementation of that right now is the LightGBM by Microsoft Research. It is very fast, and it tends to generate good results when it's properly tuned. Another option that people really like that we also tried is random forests. These are nice just because the way that it kind of generates the individual decision trees and the way it kind of bags the features, it makes them fairly high performing and fairly kind of automatic in terms of there's not that many parameters that must be tuned for a random forest for it to work well. And it's fairly robust to, let's say, missing data and things like that. And we also tried neural nets. These things, as you all know, have been used a lot. They're very flexible, very powerful. They're able to solve many problems that were considered difficult or impossible for computers just a short while ago. And last but not least, there's also the support vector machines, where you're essentially projecting basically the problem space to higher dimensions in order to find a way to kind of to find the decision boundaries. And with RBF kernel, you can actually use an even number of dimensions. So all of these were very powerful techniques, and they all did well in certain areas. When selecting a model, it's very important that the model is stable, that is efficient with the data that we feed it, just once again due to the limited amount of data we have, and that it scales well to basically large amounts of data, and you can run quickly. In the end, we actually selected neural nets, which are not the best at any of these. However, they are very good characteristics. Essentially, they theoretically at least they can solve any approximately any continuous function. They're extremely flexible. For instance, you can even attach, let's say, SVM to the end of a neural net if you wanted to. But most important of all, they just exhibit very strong predictive performance. The other methods gave fairly good results, but in most cases, it was not too different from our, hand calibrated traditional prepay model. Whereas the neural net is the one that got us really excited. The reason is because of the way they work. So because they start from simple relationships and build up to complex relationships, they can, with a large enough neural net, they can model very complex interactions between inputs. And further, because of the way they're built, right? So you start with individual neurons, which are just simple functions, and then you can kind of attach them together and make them into layers, and then also combine the layers in various ways. Basically, the first layer is always the input layer, and the last layer is always the output that you want. In between is where you can kind of be creative in terms of the architecture. At the very basic level, all a neuron is a simple mathematical function. So simple, in fact, that the most popular kind of activation function used today is the reroute, as you can see on the bottom right. It's literally just the max of 0 and x. So when x is negative, y is 0. When x is positive, y is just equal to x. Starting with this very simple function, by connecting many of these together, you can get very powerful predictive results. As you can see, there are many kinds of neural networks. Different architectures are advantageous for certain applications. For instance, convolutional neural network has been used a lot for image recognition, and then LSTMs or recurrent networks in general are good for things like generating speech, chatbots, etc. For this demo, we're going to stick with the very classic deep feed-forward network, in which the output of each layer is connected to the input of each of the neurons in the next layer. So as you can see, this is an example of a very sophisticated neural network. This is the Inception model from Google, which has won many awards for the image recognition and option detection capabilities. As you can see, it uses many types of layers, and it connects many of them to form a very strong network. So why does this work? Why do neural networks work? The basic concept is very simple. So you start with a gradient. Remember that for each neuron, you essentially have weights and biases. So no different than, say, like a linear equation. But by calculating the partial derivative for each of those, right, we have the gradient, which points us to the direction of the steepest ascent. By going the other direction, we can adjust the weights and biases to basically minimize the error. So the question is, if the machine is learning on its own, why do we even need modelers, right? Why not just throw the problem at the machine and see how it goes? Basically, while machine learning saves us from having to basically select the functional form and having to work with the parameters directly, we do now have to deal with a number of hyperparameters, which essentially kind of determine how the machine will learn. There are many hyperparameters, only a few of which are listed here that are kind of important. For neural networks, obviously, the number of layers and the number of neurons determines the capacity of the network to learn. But the capacity may not necessarily be a good thing. As you all know, as model complexity increases, it introduces overfitting. So the idea is to have enough capacity in the network to learn the problem, but not so much that it starts to fit to noise. Another thing that's very important is the learning rate. So for each learning iteration, between the expected actual result and the model calculated result, we have an error. The learning rate basically determines how fast we adjust for that error. Setting this to be too high creates issues where the network will not converge. But if it's too low, it makes training slower, and then it creates other issues like getting stuck in local minimum. Another hyperparameter that has almost intuitive impact on the training results is the batch size. So this basically says that how much of the data you use at once to determine the gradient. It could be as small as just one, or it could be the entire training set. Theoretically, it should be just a trade-off between smaller batch size, you would need more iterations, and a bigger batch size, you would need a small number of iterations. But in practice, this actually has a substantial impact even on the final results. And then obviously the choice of the activation function that we talked about before. Do you want to use rectified linear? Do you want to use kind of like a sigmoid or one of many other activation functions? How you define what the loss to be, and then what kind of regression methods you use. Some of these we'll talk about later in order to have the model fit well. So all these are considerations that must be taken into account when building the prepayment model. Last but not least, we must talk about the libraries. While it's entirely possible to build a neural network from scratch, there are already existing platforms which work very well, and they provide convenience features that are very advantageous. Obviously, there is the Google's TensorFlow, which is very popular. Right now, it's kind of almost an industry standard. A short while ago, they brought Keras, which is kind of like a high-level abstraction for building the neural nets. So even TensorFlow, you have to write a lot of kind of code just to get started. Whereas for Keras, you essentially just decide the layers, the neurons, etc. There's also like Caffe, which is used a lot in the academic world, and MXNet, which is still popular with many circles today. So in the end, we selected TensorFlow mainly because just the fact that it has the largest active user base. So whenever there are issues that come up, it's easy to find people to discuss with. It's multi-platform. It runs on like Windows, Linux, Mac, even like cell phones. It has great tools like the Tensor Board and easy checkpoints where we can kind of load a previous version model very easily. And then obviously the Keras high-level abstraction helps a lot with the model development speed. So now we'll go into the details about building our kind of this demo prepay model, and I'll hand over to Wei to talk about details.
Thank you, Fan. Now I'm going to introduce our deep learning prepayment model and how to tune our hyperparameters to get better result. And actually, our goal of our model is to project the CPR. And our model input is the long level data. It's a fixed rate, 30 years long level data from Fannie Mae and Freddie Mac. The loans vintage are from 2010 to 2017. And the factor date range is from January 2012 to June 2018. And after feature selection and feature engineering, we choose some of the features such as loan age, loan size, FICO score, LTV, refi incentive, market-to-market LTV, settle, etc. So now let's take a look at a prototype of our model structure. The picture on the left side is a basic model structure. We use a very traditional deep learning model. So actually the data flows bottom up. First, the input data first got into the first hidden layer, and then go to the second hidden layer, and then go to the output layer. After the output layer, we have estimated CPR. And we can compare the estimated CPR with our actual CPR and calculate the error. And we have to choose an optimization function to minimize the error. So that's our model structure. And people always talk about deep learning as a black box. Now let's try to open this black box to see what's in the hidden layers. So now let's take a look at what's in the first hidden layer. So the first hidden layer has 4 components. From bottom up is dense 1, redo 1, batch normalization, and the dropout. And for the first 2 components, the dense 1 and the redo 1 is the core of the first hidden layer. So let's take a look at the equation on the top right. The dense is actually the linear part of this hidden layer, and the activation, the redo is actually the nonlinear part of this activation. So the third component of this first hidden layer is the batch normalization. The batch normalization is a very useful technique to standardize the output of the first layer and use the standardized data to send it to the second hidden layer. And the fourth component is dropout. And we will talk about this regularization method later. So actually, we can open further about what's inside the components. So now let's take a look at what's inside dense. So as in the third picture, we can see that the dense is just what the function showed in the upper right. Is the randomly selected weights W times the kernel plus the bias. So this gives us a pretty good picture about what's inside the first hidden layer. So about the second hidden layer and the output layer is pretty much the same structure here. So after we build our initial result, we have initial model. We have some initial result here. So this is time series data from agency-backed mortgage-backed security from Fannie Mae. And we can see that the red line is the actual CPR, and the blue line is our model is estimated CPR. We can basically catch the trend of the CPR, but we can't catch the extreme case. So in that case, we have to tune our the hyperparameter of our model to make our model to fit much better about this. So the first class of hyperparameter we are trying to tune is the optimization method and the learning rate. So the optimization method we are choosing is called the Adam optimization method. We can see from the left picture, all those 5 optimization methods is based on gradient descent, which Fan explained earlier. But the Adam optimization method is actually gradient descent plus momentum. And the momentum will help us to find the minimum better. And it's also a partial solution to get out of the local minima. So it's a very efficient way to use in deep learning for the optimization method. And the corresponding learning rate in the Adam is also very crucial. We have to choose the right learning rate. If we choose a large learning rate, then the parameters of weight and bias will learn very fast, but we sometimes will miss the minimum, and it is difficult to converge. If we choose a smaller learning rate, it will take forever to converge, and also we will get stuck at the local minimum problem. And here is another example of how the importance of the learning rate. If we take a look at the picture on the right, if the learning rate is too large, the loss of the cross-validation set will be very volatile. So we can't get a good information from this model. But if we choose a proper learning rate, we will have a very smooth loss of the cross-validation set. And this model is what we wanted. And the second class of the hyperparameter we want to tune is the hidden units, number of hidden units, and the batch size. And hidden units in each layer is also very crucial. If we choose a very small number of hidden units, and we just can't cache all the relationships between the model inputs. But if we choose a large number of hidden units, some of the neurons might be function identically. But this is not very efficient. So we have to choose a suitable number of hidden units. About the mini batch size, and this is a way to improve the gradient descent. When we use the gradient descent method to optimize, we can update weights and bias after one sample, or we can choose to update our gradient after a whole iteration of all these samples. But those two methods are either not accurate or not efficient. So we can choose update the weights and bias after a certain number of samples. So traditionally, we choose the mini batch size equal to the 2 to the power of n, such as 64, 128, etc. That in that case, the code will run faster due to the structure of the computer memory. So the third class of the hyperparameter we are trying to tune is the number of layers, the regularization method, and the weights initialization. The number of layers is also very crucial. If we choose a very small number of layers, our model may just be underfitting. We can't capture the relationship of the inputs. If we choose a very large number, and the model might be overfitting, and some of the layers, especially the first few layers, will learn very slowly, and it will not help to improve our model. For the regularization method, we use the method called dropout. The dropout, it means that we just randomly drop out certain number of neurons in each layer, in each iteration. For example, we can take a look at the picture on the right. The dropout layer in each iteration, it will randomly drop out 50%. That means 2 neurons each time. The intuition behind dropout is that we just cannot rely on some of the specific neurons. We want every neuron has their functions. So we just randomly drop out several neurons at a time and make the weights equal. or we can use the traditional L2 regularization method to avoid some of the weights is too large in some of the neurons. And this is a very traditional method we are using for regularization. And for the third part is weights initialization. The weights initialization is a partial solution to solve the gradient vanishing or exploding problem. The gradient vanishing means that the gradient sometimes are too small, and so that the model just can't learn. And especially in the first few layers, if the weights is just constant through time, it's just learn any information, so the model is not that good. The exploding gradient is just the opposite of the vanishing gradient. So if it means that the gradient is changing too much. If the gradient changing too much, it's very difficult to converge. So for choosing the right weight initialization, we use a method which was published by He in 2015, the paper to initialize the weights. So when we are tuning the hyperparameters, we use a very powerful tool called Tensor Board to help us to visualize what's happened through each iteration. It's actually a live monitoring of the training process, and it's very easy for us to compare between each iteration. For example, the left top corner of this Tensor Board picture is the loss of the training set and the cross-validation set. Through this, we can see that if our model is training properly. And the second picture on the right is our model structure. During each iteration, we can see we can open up each of the component in each of the hidden layer, and we can have a very good idea where the data just flow. And the bottom two pictures shows us the histogram and the distribution of our parameters. And what kind of information can we get from the Tensor Board? For example, this is layer 2 bias from one of our models, the histogram and the distribution. And we can see that from each iteration, the bias histogram changed significantly. That means for each iteration, our bias can learn something from the iteration and change the distribution, so that this kind of model is good for learning. And for the right picture is the distribution of this bias. So it also shows information that the distribution has changed through iteration. So this is a good model. But for this kernel, it's not learning very well. We can see from the left picture that the histogram through iteration, it didn't change much. So it means that this kernel basically didn't learn anything from our input. So there might be something wrong with the model. So we have to dive in to modify our model. So after all the hyperparameter tuning, we can see that in the right picture, we cannot just only capture the trend of the time series. We can actually capture the peaks of the series very good. So this is the power of hyperparameter tuning. So during the hyperparameter tuning, we face some of the very common issues. For example, the convergence issue. We face some of the vanishing or exploding gradient. In this kind of like a convergence issue, we can choose to change the initial weight initialization or to solve this kind of problem. And sometimes we will face the stuck at the local minimum issue. And in this case, we will just tuning the hyperparameters or change the optimization method to try to get rid of this local minimum problem. And sometimes we will face the overfitting problem. For this overfitting problem, we just try to use different kind of regularization methods, such as dropout, and we tune the percent of the dropout, or just use to L2 regularization. And that's the hyperparameter tuning and our model structure. And now let's welcome Janet to talk about our results.
Okay, great. Thanks, Lai. So now to the fun part. How does this model actually do So as a reminder of what Lei and Sam have put together, we're looking at fixed rate 30, Fannie Freddie production, vintages covering 2012 to 2017, and then the the model build set included factor dates through the end of 2017. Here on the page we have model versus actual CPR results for last month for a variety of different coupon vintage cohorts. As you can see, the fit is pretty well, especially in the well-populated cohorts. You'll see it as you get to the tails of either low or high coupon is where there is some divergence in the absolute difference between model and actual. Going to the next slide here, we have looking at model fit and backtesting through time. So for a few select pools, we're just looking at month by month CPR, actual versus model, and then again, this is through the end of 2017. You can see certain pools, the model fit is off a little bit in certain places, but for the most part, it looks like the machine learning model has really developed such that it can get those peaks and troughs. Here's another view, which includes some out-of-time series testing. So we take the back test through the end of 2017 and then go forward into the first half of 2018. So you can see the results as we move out of the time period we use for estimating the model and then into this out-of-sample time period. So again, the model fit is looking pretty good. So on the next slide here. So what can we do with this model? So a lot of our clients, the people we speak to, are thinking about using these alternative techniques, at least initially, as challenger models. They're looking for a different viewpoint in terms of prepay results or risk analytics results, and this is, first coming into their workflows as this alternative challenger view. In the charts at the bottom, we compare our traditional prepayment model. So this is a traditional approach where we model turnover and refi incentive separately. A refi incentive has that traditional S-curve shape, and we're comparing that to our machine learning model. You can see that the traditional approach does a pretty decent job, but the machine learning approach seems to capture a few of those peak areas a bit better. So it looks like the machine learning model does a lot better, so why wouldn't you always use this? We would like to point out a couple of drawbacks to the machine learning model. First, model stability. So Lei spent a lot of time talking about the importance of hyperparameter selection and getting that right. The demonstration here with this chart is some slight changes in those hyperparameters can lead to really different model results in the end. So it's very important to get those right and to understand how tweaking those will affect your results. And then, one of the major issues, I think, with this machine learning approach is that it misses giving the model user the ability to tweak and tune and use knobs on the prepayment model results. A lot of our users are typically tuning their models using, elbow shifts, turnover shifts, other refi incentive shifts on a regular basis, using their kind of industry expertise and knowledge. These machine learning models reduce the ability of the model user to do all of those things. And this is especially important when we think about using these prepayment models in new spaces under new product types. One big one being the emergence of non-QM. If we wanted to use this model in the non-QM space, really, our only mechanism to sort of tune the model would be kind of a level shift of the results. There's no kind of nuanced way as of yet we found to do a more detailed tweaking. And then kind of like the biggest challenge for a lot of people with these models is, again, that black box nature, not understanding the results. Some of those results look really great, but, you know, is it too good to be true? You know, we want to be able to build trust with the model and have people understand it enough such that they're comfortable using it in their everyday workflow and making it a part of their decision-making processes. So, you know, we look to really help explain a lot of the inner workings of these models through analysis of the outputs of the model. So some ideas for how this could work. So it's really through analysis of, you know, what is coming out of the machine learning model that you can better understand how inputs to the model affect results, and you can build that trust that, hey, these relationships that you're finding are actually logical, are the relationships that we expect to see. So some ways you can do that. So first, sensitivity testing. So, you know, create a test suite of various inputs, change things one at a time, sort of incrementally, and then look at how your model results for CPR change for those various tweaks in the model inputs. Say, for example, you just you know, feed the model different coupon rates, and then look to see that, yes, the resulting CPRs make logical sense to you. Another kind of test suite to kind of build this confidence in the model is around negative testing or extreme value testing. Trying different combinations, perhaps at the edges of kind of a logical space of inputs to the model to see how the model reacts to these extreme values. And then the third method we have down here is LIME, or local interpretable model agnostic explanations. This, in my mind, is essentially building a simple model on your model results to help understand how the model is working. So you could think of it as, you know, focusing on a small subpopulation of your universe, you know, perturbing some of the model inputs slightly for that subspace, looking at the ultimate output results, and then essentially building a model on those output results, a simple logistic or linear model, where you can then look directly at the coefficients resulting in your model on the model, and you'll be able to see that, hey, those coefficients make sense for the relationships that I expect to see coming out. Here we just show kind of some examples of sensitivity testing on our machine learning model. So you can see in the first one, age, you can see the age ramp with, as age increases, kind of from 0 up through 20, 30, you see that ramp up of CPR. Similarly, you see it kind of that FICO relationship you expect to see as FICO moves up in the space, so does CPR. And then the relationship with average loan size. Okay, so next steps with our modeling here. So there are a couple of things where we think there could be or should be improvements. So starting at the bottom, I think there are a few features that we aren't capturing yet in our model that we know about. We, you know, went over some of the inputs to the model. We certainly capture the heavy hitters, the usual suspects in any prepayment model, but we haven't incorporated servicer in there or a few other kind of loan level details that we'd like to. Additionally, we started our focus on the fixed rate 30 population. We can sort of expand to other product types as we move forward. And then at the top, we make a few points about what we're thinking about as this hybrid model approach. So right now, we're not explicitly modeling things like burnout. We kind of feed components of what could be considered burnout into the model, and the neural net is, we think, figuring out how those things are kind of affecting the CPR results. But we could take a more active approach to these kind of elements of prepayment that we know about. So we could derive what we think is a cumulative refi incentive field and actually have that as an input feature to the neural net, and thus take a more kind of hybrid approach where we're kind of actively constructing these input fields that we think best capture prepay behavior. And then additionally, through some of this kind of active structuring of inputs to the model, we may be able to sort of help with this issue around not having knobs or tuning factors that an actual practitioner can use and interact with as they see fit, as they encounter new types of collateral or new spaces. So these are some of the next steps in our research, some of the things that we're trying to do as we move forward. So I think that's kind of about it for our kind of presentation here. We have a number of questions, I believe, which we're going to take a quick read of that came in, and we'll try to work through them as we can.
Yeah, so the first one here is, how frequently should you recalibrate a machine learning model, and what is the best practice for that?
Okay, I think I'll take that one. So basically, machine learning models, I mean, one of the, I guess, advantages some people kind of like about them is that, because they are, essentially adapting to the data, right? So essentially, they could recalibrate themselves, even like all the time, right? There's actually a method called online learning where, like, for every single data point coming in, the model calibrates itself. That's depending on the application, that may or may not be a good thing. Like, for instance, if for prepay model, if the purpose is like risk management, right? We kind of want the long-term view. We kind of want to see that the if we're saying that our duration is this, right? That it doesn't change, like, say tomorrow, right? So or significantly tomorrow. So essentially, I think, you can treat it as any other model, such that depending on the need, it could be, say, calibrated, say, a few times a year, or whenever there's a regime shift, right? But or if it's some kind of, I don't know, training application or something where it's more important to have the latest data, then it can be recalibrated almost in real time. So I guess that's that. Yeah.
Thanks, man. We got one more here. Have you compared the predicting CPR results between the random forest / boosting based LGBM XGB models and neural networks?
Okay, so basically we have that. In fact, we did prepare, like, so essentially what happened with those is that the closest we got probably in terms to neural net is the LightGBM. So, like, the gradient boosting. If you've been around for the tau community, generally speaking, like, the gradient boosting and the neural nets are kind of the top performers. In this particular case, we got, like, decent results, but, like, not kind of nothing that would really blew kind of the kind of like our expectation out of the water. We have some we have some results for LightGBM here that you can show you. So basically, these are kind of the best that we were able to do with LightGBM, and like I said, this is the most powerful gradient boosting method we found. And you can see here that it's okay, but for us, this is really not that much better than or in some cases not better than our traditional model. And then gradient boosting comes with many of the same kind of drawbacks in terms of like the black box nature, in terms of like all these other things, because here is not offering a significant kind of boost in performance. we just did not feel like it was kind of like a worthy endeavor to use it. But we do use the other method for other purposes. For instance, we have a short-term prepayment model that does use like SVM. So it does fairly well predicting, say, just 1 month ahead with a limited set of data for a specific subpopulation. And there we can get like, correlations above 97%. But for the long-term model, like the neural net is the one that really performs much, much better than the others.
Thank you. And another one just came in. So this one is, what kind of approaches do you tune your hyperparameters with grid search or something else?
Actually, I will take this one. We didn't use grid search to tune our hyperparameters. Basically, I choose the algorithm of just randomly selected hyperparameters in certain range that makes sense. And in this case, if we find out that maybe some of the hyperparameters will be good for tune, we will just enlarge that region and randomly selected some of the hyperparameters in that populated region. And this will give us a better result.
Great. Well, we're getting some really good questions here. Another one just came in. How long does it take to run calibration? Do you use a computer farm or do you run calibration locally?
Right. So for our kind of like the bigger models, well, definitely. I'm not sure if you guys are familiar with, but like basically we have an entire like edge platform that's essentially kind of our mounting platform. We use it internally as well. Basically, those are kind of like in the cloud with many GPUs and a lot of memory and things like that. For this particular application, like for this demo model, it's a fairly small model, as you can see. It's just a few layers and a few hundred neurons per layer. In this case, it runs pretty well even just on one machine. I think it takes about 3 hours with the given data set and with just a simple network. For bigger different sets, you definitely want to start using, like, for instance, like multi CPUs, multiple servers, and even GPUs to accelerate the process. But for this particular instance, running on a single multi-core machine, you probably like a few hours.
Thank you so much for that, Fan. We are going to move on to one more here. We might have time for a few more after that. So this one is this model being used live by any clients? If yes, can you elaborate on what types of clients and how?
Sure. So right now we're still in research mode, kind of fine-tuning the model. Kind of as discussed, it really just covers fixed rate 30 so far. So we're trying to incorporate that for a few other product types. In terms of uses, we do have a couple of clients who are targeted to use this initially. As we roll it out, we're working with a couple right now, and actually it's the process of building out the model. And they'll be using it initially kind of as that kind of alternative viewpoint model. And then also, a client will be using it to kind of monitor expectations kind of generally, not directly for decision-making, trading purposes, but for kind of monitoring expectations of new vintages of Fannie versus Freddie. So we do have kind of 2 live client applications where they're working with us as we build this out.
Thank you for that, Janet. Another one that we got in, that's interesting, is what is the batch size?
So I guess there's 2 ways to interpret this question. I'm not sure which way it's intended here. In terms of what the batch size is, as explained earlier, is basically just when you run through, running through one iteration in the training is called an epoch. That's how long. That's basically running the entire data set once. And then depending on your batch size, it could take 1 or any number of epochs to go through the training. So that affects 2 things. One is basically the training speed. Basically, the bigger the batch size, the the slower it takes to compute the gradient because you're averaging across many data points instead of one data point. But then in terms of like that should theoretically give you a better sense of the direction that the model should be moving towards versus using, let's say, one example. So it's like a trade-off, but in the end, actually, you do kind of have to try different batch sizes because for reasons that are not entirely understood, using different batch sizes doesn't affect just the kind of like the run speed. It also affects kind of like the final result as well. Usually not like to an extreme amount, but it's significant enough where it's worth trying different batch sizes and then and see which one works. If the question is which batch size was used in this particular model, wait, do you remember which one for this particular instance that we used?
I think we tried 64.
64. So this one was 64.
Awesome. Well, we are just about out of time, but we have a few questions that we were not able to get to, so we'll be in touch with you shortly after this. And we will answer this one. We will have a recording up live on our website probably within the next day. So thank you guys so much for taking the time to join us. We think this went really well. We hope you did too. All right. Have a nice day, everybody.
Thanks.